So now we are in part 2 of the lecture today, and this is a bit hard part, but it will be okay. So reviewing part 2. Reviewing in lecture 1, we solved our main problem EA times d2u of x by dx squared plus p of x equal to 0 using direct integration. And in the first part of this lecture, we solved it using superposition. And we end up to very nice series u of x equals sigma over u asterisk between x minus xi I times phi of xi I. Very nice series to represent my solution. In the second part, I want to use the direct integral equation to represent this solution. So I want to find u of x using direct integral equation. And then we'll start to see the difference in philosophy between the indirect way and the direct way. But now I want to generate this solution using two ways. The first way is a mathematical way via a certain integral identity. I think Paul would like to give it the name weighted residual statement. And the alternative way is to use what we call it virtual work. So these are the two main entrants to the direct integral equation. And we'll see the difference between the direct integral equation and the indirect integral equation to solve this very, very nice and very easy differential equation. Of course, this differential equation is accompanied by the shape of the beam and the boundary conditions. Before going, do you hear me, or do we have any problem? Because it's give me an message that the internet is not stable. I think everybody is hearing me. Okay.
Yes, I can hear you. Yeah.
Okay. Thank you. Before we do anything, we will revise the integration by parts. We will revise the integration by parts. To revise the integration by parts, we always give the very nice way. It is integral of u dv equal uv minus integral v du. It's very well known, and you can get it. You can get this equation direct from the product rule uv. When you differentiate this, you will get u dv plus v du, and you will end up u dv equal vu minus v du, and integrate both sides, you will get this form. It's straightforward, it's not a problem. But here, I want to read it. So this one, I'm going to call it the first function. And this, I'm going to say it is the second function. So actually, we can read it like this. It is equal to the first function times the integral of the second function minus the integral of the second function times the derivative of the first. Why I'm saying that? Because when we get involved during the course with a lot of functions together or a lot of kernels, it's much better to read it like this. The first function times the integral of the second function minus the integral of the previous integral times the derivative of the first. okay, to make things faster in the development of the mathematics itself. The second thing I want to revise, this is a domain integral. So actually, this is a domain integral. This is a domain integral. So this integral should be from 0 to L, from 0 to L, over the beam itself. And this is from 0 to L. So practically this one, we always substitute to the upper limit and the lower limit. So actually this part is a summation. So this part practically is a boundary integral. So this part here, it is a boundary integral. So it is a summation at 0 and L. Practically, we always say the upper limit minus the lower limit. From where it comes the minus, and we actually talk about the summation. So it is actually is a summation of U and V times the normal. Because the normal at x equals 0 to the beam is equal to minus 1. This is the normal. And at x equal to L, the normal is equal to 1. So practically, this square bracket, when we substitute with the upper limit and the lower limit, it is actually integral over the boundary, is a summation at the boundary points, but is not a summation as boundary points only. It is a summation of the integrands times the normal. Because of that, we say it is the upper limit minus the lower limit. Because of that, it is equal to the value of uv at L, or at x equal to L, minus the value of uv times at x equal to 0. This is mainly the minus comes from the normal, because we either the upper limit values minus the lower limit values, or the summation at the upper limit and the lower limit multiplied by the normal to get this minus. These are the two main points of the integration by parts. Okay, and we like the integration by parts mainly to change. That's the best thing here. You can say it. Look, here's the derivative on the v. We started with the derivative on the v. We end up to the derivative on u. Okay, so we moved the differential operator from one part to another part. So if my function is it has two differentiation here. It has two differentiation here. So I can move this differentiation to another function and get u. This is the idea. So three things with the integration by parts. From where it comes, and I want to read it. The second thing, it is a domain integral actually, and the first term is a boundary integral, and the summation on the boundary points with the normal to give me this minus sign. And the third thing, this integration by parts, actually it weakens the differential operator that I have. This is the best thing about the integration by parts.